So, welcome everybody. I'm Dave, and Abhishek is going to tell us a nice story about bedded surfaces, corks, and family invariants. And I will be quiet and let him take it away.
Well, thanks for the invitation. You know, like people do when they, call a radio program sometimes, they say that, long time listener, first time caller. So I'm, long time follower of this webinar series, and this is the first time participating actively. Um, this is what I'm going to talk today is joined with Okuto Kono and Masaki Taniguchi. As you'll soon see, I have fantastic handwriting. So, if you can't read anything, something's illegible, please let me know. All right, so let's begin. So we'll begin with corks. So what are corks? So definition, a cork is a tuple CY tau of a contractible four-manifold C with boundary Y. Moreover, tau from Y to Y is a diffeomorphism that does not extend over C smoothly. Okay. So here's a cartoon picture. So this is the contractible manifold C. This is the boundary Y, and there's a diffeomorphism tau on the boundary, and then you require that tau does not extend smoothly over the contractible manifold. So a couple of remarks just to begin with. Work of Friedman implies that tau does extend over C topologically. So there is a C0 extension of tau over C, but not necessarily C infinity. And then another remark is that the original definition of a cork was due to Akbulut, I think something around 92. However, the original definition differs from the one from ours that we're going to use today quite a bit. So one of the things that Akbulut required is that the corks, for example, C was Stein in his definition. So what we're calling cork today, he called loose cork, and in fact, that statement is also quite incorrect because I mean he also wanted that cork to change in line smooth structure. But for simplicity today, we're just going to refer to these tuples as corks. And then the first example of a cork was also found by Kubodot. So what is the first example of a cork? So an example. So I'll draw for you first a knot. So this is the knot 946, or also, the -3 -3 pretzel knot. So in this knot, you can see that there's a symmetry here, which is 180-degree rotation with respect to the axis that's sort of coming out of your laptop and hitting you. So if you rotate 180 degrees with respect to that axis, you'll get the knot back. So that's a order 2 symmetry of the knot. And then if you do +1 surgery on this knot, so you get a 3 manifold. Let me call it +1 surgery on 946. And then this rotation here, let me call it tau, induces symmetry on the surgeon manifold. So let me also call it tau. And then because +946 is a slice knot, it bounds a smoothly embedded disk inside the 4-ball. You can do +1 surgery on the slice disk to obtain a contractible bound on that surgeon manifold. So this is a contractible manifold. And this pair, this tuple here is the Akbalut cork. So he didn't exactly phrase it the way I'm phrasing it, but this is essentially what the Akbalut cork is. Okay. So that's an example of a cork. So really the question that we should have in our mind right now is that, why should we care about corks? And so let me motivate that by stating a theorem of Kurtish, Friedman, Shang, and Strong. And this was independently proved by Matviev in 96, where they showed that any two exotic smooth structure on a simply connected closed four manifold are related by a cork twist. Okay, so we know what corks are. I haven't really told you what cork twists are. So cork twist is the following topological operation. So suppose you have a closed four manifold X, and on the closed four manifold, you have an embedding of a tuple of a cork. So here's the boundary of the cork. So what you can do at this point is that you can sort of cut along Y, separate Y, and then reglue by the boundary twist. So if you do that, so instead of gluing it back by identity, you glue it back by the boundary twist. So that will change your underlying four manifold as a set to a different four manifold. Let's call it X upper script tau. And this operation is called the cork twist. So regluing by the boundary twist. And what this theorem here is saying that any two exotic smooth structure on a given four manifold can be related by such an embedding of a cork twist. Okay, so really then it sort of tells you that if you're interested in studying exotic smooth structures, you might as well also be interested in studying what corks are. Great. So at this point, maybe we should discuss that having sort of got a feeling of why should corks be interesting, maybe we should discuss that how to detect quarks. Okay, so how do we find a tuple that has the features of what quarks are? So I'll explain. We will discuss three different methods today. Okay, all of them as an example. We will keep the Akbulut cork example in mind as we sort of go through these different methods. Okay, so here's the first method. So this method uses what's called the exotic smooth structure. So exotic smooth structures or closed smooth four manifold invariant. So various invariants of smooth four manifolds, such as Seiberg-Witten invariant or the Donaldson invariant and so on. So this is that, this process has been the most prevalent way of detecting corks in the literature. So this is sort of the most common way of detecting corks since the 90s. So how does it work? So as promised, we're going to keep the Akbulut cork example in mind. So the Akbulut cork. The way Akbulut proved this is the cork is that he showed that there is an embedding of this cork. Well, again, this is a slight reformulation of the way he showed it, but I think it captures the underlying essence. So there's an embedding of this cork into blown up K3 surface. And then if you reglue by this Akbulut cork by the cork twist, then Akbulut showed that this underlying four manifold changes from K3 blown up. Sorry, this is CP2 bar. K3 blown up to 3 CP2 connects some 20 CP2 bars. And then the Seiberg-Witten invariant for blown up K3 with respect to one particular spin C structure that comes from the canonical spin C structure is non-zero, whilst a Seiberg-Witten invariant of 3 CP2 connects some 20 CP2 bar with respect to any spin C structure is always zero. So that actually tells you that, well, suppose if tau does extend smoothly over C, then you'll get a diffeomorphism between these two manifolds. But then they should have equal Seiberg-Witten invariant. So that shows that tau cannot extend over C smoothly. So this is how, in essence, he showed that the Akbulut cork is actually a cork. Okay, so really what happened here is that in order to show that something is a cork, we used exotic smooth structures or a closed four manifold invariant here. But however, as you see, the reason we sort of get interested in corks is that it seems to tell us that you can capture what two different exotic smooth structures are by knowing what sort of corks are. So ideally, you'd hope to get a four manifold invariant free method of detecting corks. Okay, so let's now talk about the second method. So before we can get to the second method, let me now again make a definition. So this is something that's called a strong cork. So this is due to Lin, Ruberman, and Savelyev. So a strong cork is a pair y comma tau of integer homology sphere y with a diffeomorphism tau such that tau does not extend over any Z homology ball W with del W equal Y smoothly. Okay, for consistency reasons, we also require that that exists a contractible 4 manifold C such that C y tau is a cork. So any strong cork is a cork, and then it satisfies this external property, which is well, what is the definition of a cork? The cork was this diffeomorphism tau is not going to extend smoothly over a given contractible bound. So strong corks are, well, you don't need to fix the contractible bound. You just say that, well, W could be like any homology ball. Okay? Not necessarily a fixed contractible bound, and there will be no C infinity extension of tau to let W. So this sort of emphasizes on the fact that maybe the phenomena that sort of dictates that non-extension of a boundary diffeomorphism is sort of a completely three-manifold phenomenon. And indeed, Lin, Ruberman, Savelyev showed that Akbulut cork is strong. Okay. We're not going to get into how they proved it, but let me just mention that they also used four manifold invariants. Okay, so now let's discuss the second method. This was somewhat of an aside. So in 2020, together with Dye and Hayden, we gave a four manifold invariant free method for detecting strong quarks. Okay, so very briefly, what went underlying to this method was that, given any diffeomorphism on Y, there is an associated action on the Heegaard-Floch chain complex of Y. So what we did is that we followed involutive Heegaard-Floch homology to give an invariant, and that sort of looks like certain pairs of equivalence classes of consider the pair of the chain complex, the Floch chain complex, with the action of the diffeomorphism, and then you quotient out by certain equivalence relation. And then if you can show that this equivalence class is non-zero, where non-zero is in quotes, because I haven't really explained what I mean by this, then that implies that Y comma tau is a strong cork. Okay. So throughout, we're going to sort of subsume the fact that whenever we are talking about strong cork, it's actually a cork. I'll just focus, and when I say that this is something a strong cork, it just means that tau is never going to extend over any homology ball that Y may bound. Okay, so as promised, we should connect this to the example of the Akbulut cork. So here's how we can show that Akbulut cork is a strong cork. So let me draw again for you the previous picture that we had drawn before. Okay, so this was again the 946 knot. And this was the cork twist. So what we do is that we construct a negative definite cobordism from +1 surgery on 946 to manifold, which is given by attaching these two -1 framed two handles. So the outer end of this negative definite cobordism is going to be another three manifold, which you can observe by if you blow down these two -1 framed handles, you'll get a different knot. Okay, a little inspection will tell you this knot is actually the figure 8 knot. Okay, and then still doing +1 surgery on it. So this is a cobordism that has that is sort of negative definite, and it's sort of equivariant with respect to this rotation 180 degree rotation tau. So the tau action actually extends over that negative definite cobordism. Plus one surgery on the figure 8 knot can also be identified with the B-span sphere 237, sigma 237. So a consequence of this geometric fact is that this equivalence class that I was alluding to earlier is less than or equal to, again, let's say in quotes, to the equivalence class of sigma 237 with the corresponding tau action. And then you can compute explicitly this equivalence class because the floor homology of sigma 237 is really simple and show that it's actually strictly less than 0. So this follows from, either from the work with Dye and Heron, or you can also apply the equivariant surgery formula. To show that this class is, strictly less than 0, which in turn implies that this class is non-zero, which then implies that, plus one surgery on 946 with the action of tau is a strong cork. Okay, so a couple of remarks is that we did not use any four manifold invariant to produce this strong cork. The only thing we used was this involutive Hegel homology package and sort of like analysis of actions of diffeomorphisms on the floor chain complexes. Okay, so this sort of approach has been sort of useful in many other situations. So for example, a slight refinement of this approach was used by Dye, Kang, myself, Park, and Stroffergen to show that the double branch cover of the 2-1 cable of the figure 8 knot with the covering involution is a strong cork for Z2 homology walls, which implied that the 2-1 cable of the figure 8 knot is not smoothly sliced. And this sort of showing that this double branch cover is a strong cork was only possible because we didn't have to rely on any four manifold invariant. We could use this sort of approach to show that something is a strong cork. Okay, so that's all I'm going to say about the second method. So let me now come to the third method. So this third method is joined with Kono, myself, and Taniguchi in 23. So we sort of give a criteria for producing strong corks, and here's the criteria. So let Y phi be a integer homologeous sphere Y with a diffeomorphism E. Suppose that there exists a smooth four manifold X with boundary of X being Y. Moreover, let B1 of X be 0 and B plus of X be 1. Now, if phi preserves a spin C structure of X and reverses the orientation of H plus of X. So H plus of X, recall, is a certain choice of maximal positive definite subspace of the intersection form. Of H upper 2 of X with respect to the intersection form. And certain grading shift associated with that spin C structure is positive, then that implies Y comma phi is a strong cork. Yeah. So this is a lot of things. So let's sort of slowly unpack this. Again, maybe by looking at the example that we sort of have in mind, which is the absolute cork example. Okay, so what has to happen is that I'm supposed to have a bound for the boundary of the cork that satisfies these conditions, and then I know that the boundary is a strong cork. So we just discussed that +1 surgery on 946 admits a negative definite cobordism to sigma 237 with tau action. So this cobordism here has intersection from -1, -1. And then we saw that this is also equivariant. So the tau action here extends and goes to the tau action there. Now, sigma 237 has a bound on the right-hand side that has intersection from -E8 plus H. This is the complement of the Milner fiber in K3. So inside the K3 surface, if you look at the complement, you'll get a bound for negative sigma 237 that has the intersection from -E8 plus H. And moreover, by construction, you can check directly that the boundary diffeomorphism here, in this case, the tau action, it's going to extend over this bound and will reverse the H plus of this manifold. So now, if you pick a spin C structure such that it corresponds to the generator, such that in here, in the cobordism here, the negative definite cobordism, it corresponds to the generator of -1, -1. And then in this part here, this is a spin bound. So we'll pick the spin, the underlying self-conjugate spin C structure. And you sort of concatenate these two spin C structure and the spin bound spin structure on -E8 plus H. Then you can check that the overall underlying grading shift is going to be indeed positive. So what will happen is that this part here, there will be no grading shift. Whilst on this part here, it's a spin, so the only contribution is going to come from the signature. The signature here is negative, but we have a negative sign up front, so there will be a positive shift. Okay, so this implies that +1 surgery on 946 with the action of tau is a strong cork. So here as well, we didn't quite use, so these sort of obstruction, these sort of Rorschach type inequality uses what's called the family Seiberg-Witten theory over S1. The underlying idea is that you sort of form a family of that comes from the mapping torus of the diffeomorphism phi. This was prior sort of the most of it, the bulk of the work was sort of already done by the work of Kono Taniguchi, as well as Baraglia. Around 20. I'll again point out that not only we didn't have to use any four manifold invariant, but in this case, the detection of the strong cork was like somewhat like readily achieved. All you had to do is compute intersection form of certain bound, and that's it. There's nothing else to it. We didn't even also had to analyze what the action of tau is on the floor homology of sigma 237. So this also does not use any floor homology of. So this is, you just construct a bound and this rarely tells you that this is a strong cork. I'll end by saying that this method recaptures most of the existing strong corks. In other words, this is not really special about the absolute cork. Any strong cork that exists from this prior method here will also be recovered by this method. In particular, this gave a reproof of the fact that the 2-1 cable of the figure 8 knot is not smoothly sliced using this sort of approach. Okay, so I think that is all I'm going to say about corks. We're exactly halfway through, so let me switch chapters and talk about exotic surfaces. So what about exotic surfaces? So firstly, definition, a pair of surface S1 and S2 embedded in a closed, it doesn't necessarily have to be closed, but just to say it's closed for now, it's closed for manifold, are said to be exotic if there exists a topological, an ambient topological isotopy of X taking S1 to S2, but there is no such smooth isotopy. So here we think of closed surfaces. A slight reformulation of this definition is, say something is equivalent exotic surface are pair of exotic surface that are related by a diffeomorphism of the underlying four manifold. So f of S1 is S2. So the study of exotic forms, exotic surfaces have been going around for a long time, have been widely studied since the 90s. I'll not attempt to mention all the work because I'm absolutely sure they're going to miss a lot of people, a lot of important work. So instead, let me try to mention perhaps one of the first results on closed exotic surfaces, which was by the work of Finashin, Rek, and Viro in '87, showed that there exists an exotic pair which comes from tenfold connect sum of RP2 inside the four-dimensional sphere. And maybe to capture some sort of recent progress, let me mention a work of Miyazawa, who I think last year showed that, so last year or the year prior, I forget, that there exists an exotic RP2 embedded in S4. Okay. So most of the work, most of the work studying exotic surfaces focused on non-equivalent exotic surfaces. This is due to the fact that the most prevalent way of detecting exotic surfaces have been going through most of the methods factored through, and in quite analogous to the study of corks, exotic smooth structures and or four manifold invariants. So you show that two surfaces are exotic by showing that you do some topological construction to the complement, and you show that they can't be possibly related by diffeomorphism. And that sort of obstructs some of the existence of a smooth isotopy, but it's really sort of obstructing a non-equivalent exotic surface. So recently, the work of Baraglia and Oakley have also produced exotic equivalent orientable surfaces. So the underlying tool that they use is slightly different from the tools used here. So what they use, what's called an adjunction inequality for family Seiberg-Witten theory. So family Seiberg-Witten adjunction inequality. There has been many other works sort of go along this line of producing exotic surfaces that are equivalent. All right. So now let us take an example. So maybe we'll go through one example of how exotic surface detection have played around. Perhaps something that is sort of relevant to us today. So here's an example. So suppose that Cy tau is a cork embedded in a 4-manifold X. Okay. So there's an embedding of Cy tau in X. Moreover, suppose that the cork twist is killed after stabilizing by CP2. Okay, so what this means is that there's a diffeomorphism of C connects some CP2 to C connects some CP2, such that this diffeomorphism, when you restrict to the boundary, it is the cork twist. So the cork twist does not extend smoothly to the C infinity. There's a diffeomorphism. The cork twist does not extend smoothly over C, but if you connect some CP2, there will be a smooth extension. Something to keep in mind, that's the Akbulut cork. Akbulut cork satisfies this condition. In other words, it is killed by after connecting by a CP2. In fact, most of the known corks, the simple known corks, always get killed when you connect some by a CP2. So the following construction is sort of due to Mallick and Oakley, Kim, Melvin, and Ruberman. So what they suggest is that, well, because the tau action extends over C connects some CP2, and there's an embedding of C inside X, what you can do is that you can first, using the extension of the cork twist action, construct a diffeomorphism between X and twisted X. Now, inside CP2, there is a sphere CP1. Inside this CP2 here, there's also a sphere CP1. So you can pull back this CP1 to this X connects some CP2 by this diffeomorphism. Now you're going to have two different spheres here. But if you blow down this CP1, you're going to get X back. Whilst if you wanted to blow down the pulled back sphere, then you can either, instead of doing that, you can just go forward by the diffeomorphism and blow down this one, and then you'll get X tau. But X and X tau, if you assume that they're not diffeomorphic, in other words, the cork twist changes the smooth structure. Again, for a certain X, this is always true for the absolute cork, as we did see earlier. Then that implies that this sphere CP2 and the pullback sphere by the diffeomorphism cannot possibly be diffeomorphic. They're related by diffeomorphism of X connects some CP2. Because if they were related by a diffeomorphism, then the underlying, once you take the blowdown, the resulting manifold should be diffeomorphic. So this implies CP1, and let me denote this by F, and F inverse CP1 are exotic. Okay, so let me make a definition here. Maybe I should have mentioned this earlier. The situations where you have an embedding of a cork and the cork twist in fact changes the underlying smooth structure, you call it an effective embedding of the cork inside the 4-manifold X. Okay, so a couple of things to keep in mind about this construction. The first thing is, firstly, this produces two exotic spheres that are these are non-equivalent. In fact, the obstruction is literally that they cannot be related by diffeomorphism of X connects some CP2. And the second thing that is used is that the fact that cork was embedded effectively was crucially used. So if you see here, this is sort of translates to the fact that these two manifolds are not diffeomorphic. Now, these sort of operations that you do something and you change the underlying smooth structure, and you say that as a consequence, you say that two related surfaces are not smoothly isotopic, has been known around for a long time. But you can ask the following question: is that what if you're in a situation where you have an embedding of a cork in a 4-manifold, but somehow this resulting manifolds X and X tau are in fact diffeomorphic? What can you say about the surfaces sort of residing inside some sort of cork that you've twisted along? So I'll sort of refer to these sort of surfaces that are obtained by connect summing my cork with a CP2 or maybe some other manifold as surfaces associated to the cork. So these examples are exotic surfaces that are associated to an effective embedding of a cork. So the fact that we have an effective embedding told you that those are exotic. So in the work with Kono, Self, and Taniguchi, 24, we showed that there are exotic spheres associated, equivalent exotic spheres to a non-effective embedding of a cork. So it is possible somehow not to use the fact that the cork twist is actually, doing something to the underlying smooth structure. In fact, you're in a situation where it's not going to change it. It's gonna, not going to change the underlying smooth structure, but somehow you'll be able to still produce exotic surfaces from it. In fact, they will be equivalent exotic surfaces. Okay, so how do we do this? So we'll take a brief aside and we'll talk about a different result. There's something that's called exotic commutator. So what do I mean by an exotic commutator? So I'll state an obstruction and then I'll explain. So suppose that X is a 4-manifold with boundary X is Y. Let B1 of X be 0, B plus of X be 2. Moreover, suppose that there exist two diffeomorphisms, F1 and F2 of X, well boundary, such that F1 acts as the diagonal matrix -1, -1 on H plus of X, and F2 acts as the diagonal matrix 1, -1 on H plus X. Moreover, both preserve a spin C structure of X. Okay, so maybe here I should mention that let's consider Y to be an integer monosphere, the boundary of X being an integer monosphere. So they both preserve a spin C structure X. Then if, again, the associated Rorschach type grading shift is positive, then that implies that F1, the commutator diffeomorphism of F1 and F2. F1 and F2 are both diffeomorphisms of X well boundary, so their commutator is also a diffeomorphism of X well boundary. This is not smoothly isotopic to identity. All right. So we are going to, so firstly, let me explain what do I call this exotic commutator is, because, you can think of situations where this is an exotic diffeomorphism of the underlying form manifold, that we have a diffeomorphism that is not smoothly isotopic to identity, but it is topologically isotopic to identity. And in fact, these diffeomorphisms constructed in such a way so that this commutator here is going to act trivially on homology, and hence there will always be a topological isotopy of the identity. And so these sort of diffeomorphisms that are formed as commutators of diffeomorphisms are interesting because typically exotic diffeomorphisms are detected by considering a homomorphism non-triviality of a homomorphism going from G to some other group A. So this G here is a subgroup of the mapping class group. And this A here is some abelian group. Okay, so at least like before 2023, the way people found exotic diffeomorphisms was going through this route. But these sort of constructions obviously descend to abelianization of G to A. So in particular, you cannot detect exotic diffeomorphisms that are of the form of a commutator. So typical methods that sort of go through these sort of route doesn't quite work, but this sort of obstruction that I detailed here gives you a way to detect exotic commutator diffeomorphism. So this was gotten by considering a family over T2, and then sort of producing similar Faucheux-Tave inequality. Okay, so why did I mention that result? So let's consider an example of what? Of this claim that there are equivalent exotic surfaces associated to non-effective embedding of a cork. So just to be consistent, I'll still work with the equivalent cork. So recall that we have constructed these sort of manifolds before, where we had a negative definite cobordism from +1 surgery on 946 to sigma 237. Sigma 237 has a bound on the other side that looks like that has the intersection from negative E8 plus H. Now, +1 surgery on 946 has a contractible bound here. Now, let's sort of analyze this manifold a little bit more carefully. Let me call this manifold X, this closed Tor manifold. So tau extends over this negative definite bound. Tau also extends smoothly here. We do know that tau reverses the orientation of H plus here, as we discussed before. There's nothing H plus here. So now what we're going to do is that we're going to sort of connect sum S2 times S2 to the contractible bound. Okay, so now we discussed before that tau for the absolute cork extends, it's killed once you connect some by CP2. So this fact is in fact also true when you connect some by S2 times S2. So if you connect some in S2 times S2, this lithium, there is an extension of the cork twist to the boundary. So in particular, tau here extends smoothly as well. Okay, so now the underlying manifold is X connects some S2 times S2, and it is then equipped with a diffeomorphism, which I'll denote as capital Phi, which is the concatenation of this diffeomorphism, and this diffeomorphism. Okay, so now let's consider a sphere embedded in S2 times S2. What is this sphere? So let delta denote the diagonal sphere. So by this I mean a sphere representing the homology class S2 times point plus point times S2 inside the secant homology of S2 times S2. Okay, so I'll have an embedded sphere, let me call it by delta, and then the claim is delta and phi delta are equivalent and exotic in X connect some S2 times S2. And in fact, like they are equivalent and exotic in this part here. Real boundary, hence they're exotic in X connect some S2 times S2. Sorry about that. The fact that they're equivalent is obvious because they're related by diffeomorphism. Why are they exotic? And let me now sketch the proof. Why is this fact should be true? So suppose that delta is isotopic, smoothly isotopic to phi delta. Well, then we show that you can then consider a diffeomorphism of the underlying four manifold X connects some S2 times S2, which is given by the Seidel-Dane twist. On the underlying sphere. And the fact that the underlying spheres are C-infinity isotopic, that will tell you these two Seidel-Dane twists are C-infinity isotopic. So Seidel-Dane twists are, this is a particular diffeomorphism of the cotangent bundle of S2 implanted to the four manifold. In fact, their support sort of lies in a neighborhood, a regular neighborhood of the underlying sphere. This, I'm not going to get into much of the construction, but these sort of construction can only happen if your sphere has self-intersection plus or minus 2. Anyway, so if the underlying spheres are C-infinity isotopic, then we get the corresponding diffeomorphism, which are Seidel-Dane twist on those two spheres, and they are also C-infinity isotopic. Now, by construction, Seidel-Dane twist on phi of sigma is phi inverse d delta phi, which in turn implies that the commutator of d delta and phi is C-infinity isotopic to its entity. But however, by construction, you can take that phi. So phi, reverses the orientation of H plus here, because phi in fact comes from the extension of the tau on the right-hand side, which you in fact use in the beginning, if you remember the third different method of like producing quarks, that it reverses the orientation of H plus here. You can assume that by post-composing that it will preserve the orientation of H plus on the right-hand side. And whilst T delta, by construction again, so this has a homological formula, Seidel-Dane twist, and you can show that by construction it will reverse the H plus, and that is associated to H2 times S2. And because it is supported in, sidal dentist is supported near the neighborhood of the spheres here, it is extended as an identity in this entire thing. In particular, it will preserve the orientation of H plus on this side. So T delta and phi acts as diagonal -1, 1, and diagonal 1, -1, respectively, with respect to some basis. And moreover, you can pick a spin C structure here. Well, what spin C structure will you pick? Well, again, we know that there's a spin C structure that is preserved by, if you take the generators of -1, -1, and a spin here, then this extension to the right-hand side preserves the spin C structure. Well, you can take the spin structure of S2 times S2, so you'll get a spin C structure that's preserved by capital phi. And T delta as well, well, again, because there's a spin here and it's extended as identity and throughout, it'll also preserve that spin structure. And both preserve a spin C structure, a particular spin C structure, not just some random one. So this tells us that the underlying condition of the exotic commutator that I wrote down earlier here is satisfied. And indeed, we saw before that the underlying grading shift here was positive. In fact, I mean, this manifold that we're considering right now, it's not much of a difference from the manifold that we considered before for quark detection, except we've sort of attached something here. This piece has no contribution. But chunk class square minus signature rate is positive, which implies this is a contradiction to the fact that that the commutators are C infinity isotopic to identity, which implies, well, why is this a contradiction? Because we assume that these two manifolds are C infinity. I mean, these two spheres are smoothly isotopic. Okay. And why are they topologically isotopic? Well, let me just mention that, here, although tau does not admit a smooth extension over C, there is a topological extension over C, even without the S2 times S2. So you can use the topological extension, connect some by identity with the S2 times S2 part, and post-compose that with phi to obtain a topologically trivial, a homologically trivial action on, so let me write phi compose tau tilde connect some identity. This is a homologically trivial action on C connect some S2 times S2, which is identity on the boundary. So that'll tell you by Orson and Powell that there exists an isotopy, topological isotopy relating these two manifolds. Okay, so that's how we show that these two manifolds are exotic. Okay, so a couple of remarks here. The first remark is that this manifold here, this manifold has B plus 2. This is B plus here, and there's another B plus here. So B plus of X connects some S2 times S2 is 2. So in particular, the family adjunction type results cannot be applied. For this detection, because family adjunction, sort of the family Seiberg-Witten invariants are sort of well defined when B plus is greater than or equal to 3. So you cannot use the prior results to sort of think equivalent surface detection results that Oakley or Baraglia used for this particular detection. And moreover, if you look closely, apologies for too many things that's going on in this picture. Well, so let's see. So if you look closely here, if you forget about this S2 times S2, this manifold X, the quark twist diffeomorphism tau on the boundary in fact extends to the right. Because it extends to the right, you can use this to construct a diffeomorphism between X and X tau. So the original embedding of C inside X was a non-effective embedding. So these sort of produce this approach that I've sort of detailed here, sort of produce exotic surfaces associated to a non-effective embedding of a cork. There is no way that you'll be able to use the, somehow the fact that the cork twist here is changing the underlying smooth structure. In fact, it is not changing the underlying smooth structure. So to my knowledge, since the cork was sort of first found in 1990s, I mean, the understanding that why are corks useful is the first thing that we wrote down when we're discussing in the first chapter was, corks are useful because they detect exotic smooth structure. To my knowledge, this is the first instance where a non-effective embedding of a cork turns out to be useful. So in particular, there are uses of corks, even in the situations where it does not change the smooth structure. We already did see there are uses of the cork where it does change the smooth structure. Apart from changing the smooth structure, it sort of detects exotic surfaces. We saw an example in the very beginning of the exotic surfaces chapter. But it turns out that if you have a non-effective embedding of corks, that can still turn out to be very useful. I found this very interesting. Okay, so let me end by mentioning one more result from the same paper, which is there are exotic equivalent RP2 associated to non-effective embeddings of corks. Okay. So this is used in completely different. This is proved using a completely different tool that comes from real Seiberg-Witten theory. This is not the exotic commutator detection that I talked about earlier. And okay, I'll stop here. Thank you.